जैसे लीनियर एसएचएम होता है, क्या वैसे एंगुलर एसएचएम होता है? नमस्कार, वेलकम टू द स्पेक्ट्रम एकेडमी. This is online session for 12th standard. The topic name is oscillation, and today we are going through the angular SHM. अगर एक डिस्क मैंने कंसीडर कर ली और उस डिस्क को अगर मैं रोटेट करता हूं किसी एंगल के अराउंड, एक एक्सिस के अराउंड कुछ एंगल से मैं उसे रोटेशन कर दूंगा, यानी मैं कुछ एंगुलर डिस्प्लेसमेंट दे रहा हूं उसे, और आफ्टर दैट आई रिमूव माय हैंड. फिर मैं क्या देखता हूं कि वो जो डिस्क है वो एक्सिस के अराउंड कुछ ऑसिलेशंस परफॉर्म करती है, और इस ऑसिलेशंस को हमने नाम दिया एंगुलर एसएचएम. जैसे हमने लीनियर एसएचएम में देखा था कि लीनियर एसएचएम ऐसा होता है कि जहां जो रिस्टोरिंग फोर्स है which is directly proportional to the displacement from the mean position, and the restoring force and the displacement act along the opposite direction. Similarly, in the angular motion, in angular dynamics, we will see the SHM, that means we will see the angular SHM, in which the function of the force in linear motion is replaced by the function of the torque in angular motion, and the function of the linear displacement is replaced by the function of angular displacement. Now I have pasted here some animation video. In this you can see we have a disc with some radius, and if suppose this is the axis of rotation of the disc and this is the mean position. Now I am giving some angular displacement in that direction with my hand to this disc. Then you can see this is the disc. Now I am giving some angular displacement in that direction. You can see the oscillation about the mean position. That oscillations are called as the angular oscillations, and the entire motion is known as the angular simple harmonic motion. अब यहाँ पर हम देख सकते हैं कि जैसे मैंने यहाँ पर कुछ फोर्स अप्लाई किया, कुछ डिस्प्लेसमेंट दिया, फोर्स इस डायरेक्शन में लगाया, तो एक कुछ रोटेटिंग टॉर्क प्रोड्यूस हो रहा है. अब इस रोटेटिंग टॉर्क को मुझे क्या करना है, कुछ बैलेंस करना है. तो मेरी स्ट्रिंग ने क्या किया, एक रिस्टोरिंग टॉर्क, ये स्ट्रिंग लगा रही है इस डिस्क पर, एक रिस्टोरिंग टॉर्क लगा रही है. वो रिस्टोरिंग टॉर्क और ये रोटेटिंग टॉर्क क्या हो रहा है, इक्वल हो रहा है, और ऑसिलेशंस होने जा रहे हैं. राइट. सो यहां पर हम देख सकते हैं, यू कैन सी दैट हियर द टॉर्क, द रिस्टोरिंग टॉर्क, जो रिस्टोरिंग टॉर्क स्ट्रिंग प्रोवाइड कर रही है, इज डायरेक्टली प्रोपोर्शनल टू द एंगुलर डिस्प्लेसमेंट. जितनी ज्यादा एंगुलर डिस्प्लेसमेंट होगी उतनी ज्यादा टॉर्क स्ट्रिंग लगा रही है, रिस्टोरिंग टॉर्क. ओके. सो नाउ यू कैन सी इफ आई एम गिविंग द change in angle in that direction, means the direction of angular displacement in that direction, then the string is providing torque in reverse direction, means towards the mean position. अगर मैं डिस्प्लेसमेंट अवे फ्रॉम मीन पोजीशन कर रहा हूं तो रिस्टोरिंग जो टॉर्क लगने वाला है वो टुवर्ड्स मीन पोजीशन लग रहा है, यानी एंगुलर डिस्प्लेसमेंट एंड द रिस्टोरिंग टॉर्क बोथ आर इन द ऑपोजिट डायरेक्शन. सो there is a minus sign here. The minus sign denotes that the torque and the restoring torque and the angular displacement both are in the opposite direction. अगर ये इक्वेशन हमें कुछ मोशन सॉल्व करने के बाद मिल रहा है कि टॉर्क इज डायरेक्टली प्रोपोर्शनल टू माइनस थीटा, then that motion is 101% angular simple harmonic motion. Now let's some constant see the proportionality constant, then we can get tau equals to minus c theta, where c is some restoring constant. It is a rotational constant in that equation. Then, but we know from the knowledge of rotational dynamics, the torque is given by torque equals to some moment of inertia I and some angular acceleration alpha. But the angular acceleration can also be written as d2 theta upon dt square. So the torque can be written as torque tau equals to I d2 theta upon dt square. So that we can write the general differential equation for the angular SHM in the form. If we replace the torque in this equation with this format, then we can get I d2 theta upon dt square. I d2 theta upon dt square, that means torque, equals to minus c theta. Then we can get I d2 theta upon dt square plus c theta equals to 0, so that the d2 theta upon dt square plus c upon I theta equals to 0, and I can say this quantity as some omega square, so that the final differential equation of the angular SHM is given as d2 theta upon dt square plus omega square theta equals to 0. This is the differential equation for angular सिंपल हार्मोनिक मोशन. अब इस टर्म में जो ओमेगा स्क्वायर है, द ओमेगा हियर इज द एंगुलर वेलोसिटी ऑफ द रिवोल्यूशन ऑफ द ऑसिलेशन, एंगुलर वेलोसिटी, एंड the omega square we get, omega square equals to c upon I, some rotational constant and the moment of inertia r, so that we can get omega equals to under root of c upon I, right? So if we know omega, then we can find the period, because omega equals to 2 pi upon capital T. So omega equals to under root of c upon I. So we get some equations. Omega equals to under root of c upon I, where c is the some rotational constant and I is the moment of inertia. Also the time period is given by 2 pi upon omega, so equals to 2 pi upon under root of c upon I, that means 2 pi under root of I upon c. This is the time period for angular SHM in the given problem. Now we can replace c and I in some way, because we know that the torque equals to I alpha, but इन मैग्नीट्यूड इक्वल्स टू सी थीटा. अगर मैं यहाँ पर माइनस साइन नहीं कंसिडर कर रहा हूँ, क्यों? क्योंकि माइनस साइन सिर्फ डायरेक्शन के बारे में हमें पता रहेगी. इफ टॉर्क इक्वल्स टू आई अल्फा, दैट मींस आल्सो इक्वल्स टू द सी थीटा, बिकॉज टॉर्क इज डायरेक्टली प्रोपोर्शनल टू थीटा. So from this equation we can find c upon I equals to alpha upon theta. You can see this thing. So c upon I equals to alpha, c upon I equals to alpha upon theta, so that we can write the omega equals to c upon I. C upon I means alpha upon theta, because from this you can get alpha upon theta equals to c upon I. So omega, angular velocity, equals to under root of c upon I equals to under root of alpha upon theta. So this is alpha upon theta. And similarly we can write the period in the form 2 pi under root of I upon c, means I upon c is theta upon alpha. This is the expression for the period of SHM in terms of angular acceleration and in terms of angular displacement, that is theta. अब इस मोशन का कुछ हम एप्लीकेशन देखते हैं कि ये मोशन कहां पर हम देख सकते हैं. दैट मीन्स हाउ कैन वी विजुअलाइज द एंगुलर SHM in practical way. So you all people know the simple pendulum, right? So in that simple pendulum, consider some simple pendulum. It is performing some motion about its axis and it is performing motion in this plane, in the plane of the board. Now suppose this is the angle of vertical, suppose this is vertical this is the line of vertical. You can see that this is theta. There is some angular displacement. This is the mean position. There is some angular displacement from the mean position. अगर मैं कंसिडर कर रहा हूं इस सिंपल पेंडुलम को, सपोज दिस इज द मीन पोजीशन एंड दिस इज some mass, this is the angle theta, and let us consider the length of the simple pendulum is L and the mass of the bob is m. Then you can see that the forces acting on the bob are, for the first force is gravitational force moving in the acting in the vertically downward direction, which is of the magnitude m into g. In the string, the force tension acts there, right? We can split this mg in the two components. The first component here is mg cos theta and the second component here is mg sin theta. So there are two components of the force mg. In the direction of the tension, the force is mg cos theta and here the force is mg sin theta, right? So we have two forces. First one is this one mg cos theta and second one is this one mg sin theta. So basically, if this is the pendulum, this is the axis of rotation around which the rotations are performed, and you can see, if suppose this is bob, here the force is mg sin theta, right? And here the tension and here the force is mg cos theta. So there are two forces. The net centripetal force, equals to, let's say, F1 is T minus mg cos theta, and the second tangential force equals to F2 equals to what is mg sin थीटा. अगर एक ऑब्जेक्ट है, वहां पर दो फोर्सेस एक्ट कर रहे हैं, यानी एक फोर्स है T minus mg cos theta and second one is mg sin theta, and the motion is angular, that means the motion is rotational motion. अगर फोर्स है तो 101% क्या आता है, मोमेंट ऑफ फोर्स आता है, बिकॉज वो फोर्स कुछ एक्सिस ऑफ रोटेशन के साथ कुछ लग रहा है, राइट? सो मोमेंट ऑफ फोर्स आएगा. लेकिन मोमेंट ऑफ फोर्स यानी टॉर्क मींस देयर विल बी टू टॉर्क. द फर्स्ट टॉर्क is due to the force F1, the second torque is due to the force S2. So the torque is tau 1 and this torque is tau 2. Now the radius vector is nothing but the length of the pendulum, because this is the rotational motion, this is axis and this is the rotational motion. So this is the circular rotational motion. So this is the R, that means length of the pendulum. So in the first we can see that the angle between, if suppose this length is the radius vector, so in the first point the angle between R bar and F1 bar, the angle between R bar and F1 bar, you can see that R bar is this vector and F1 bar is also this vector. So R bar and F1 bar are both in the same direction. So the angle between them is 0 degree. Theta is 0 degree. So the torque here is torque R F1 sin theta. As theta is 0, sin 0 is 0. So torque tau 1 is 0. So this torque is 0. The second one is the force F2, which is in tangential direction like this. The angle between R bar and F2 bar is nothing but theta equals to 90 degree. So R bar and F2 bar, the angle between these two forces is theta equals to 90 degree. Now you can see that the torque due to this force F2, that means the torque due to mg sin theta is tau 2 equals to R F2 sin theta, but sin 90 is 1 because theta is 90 degree. So that means R F2, but R is the length and F2 is mg sin theta. So the total torque is nothing but L mg sin theta. This is the torque, L mg sin theta. So the total torque in this angular motion, in this rotational motion acting on the bob of mass m is nothing but just only mg L sin theta. Rest all the torque are 0, but the total torque is tau 1 plus tau 2 equals to mg L sin theta. अब मैंने इस इक्वेशन में और इस क्वेश्चन में बॉब पर कितना टॉर्क लग रहा है ये मैंने फाइंड आउट कर लिया कि टॉर्क लग रहा है mg L sin theta. The torque is due to only just tangential force, not this force, because the angle between this force and the radius vector is theta equals to 0 degree and sin 0 is 0. But the angle between this force and the radius vector is 90 degree and sin 90 is 1. So the torque is generally R into F2. R is the length, that means L, and F2 is mg sin theta. So the torque which is capable of doing some rotational motion is just only mg L sin theta. So इस equation में, in the question of simple pendulum, we know that the torque is mg L sin theta. Now we will consider only that torque. So in the motion of simple pendulum, the torque we get mg L sin theta, where L is the length of the pendulum of the string and m is the mass of the bob and the theta is the angle of the string with the vertical. So mg L sin theta, this is the torque. But torque equals to what? I alpha, we know. So we can equate this I alpha equals to mg L sin theta. अगर मुझे simple pendulum study करना है तो angle that the theta should be small so that we can see the exact oscillations. Angle क्या चाहिए? Small चाहिए, ये भी पता है. And if angle is the small, then sin theta of small angle approximately is theta. So we can take sin theta is approximately theta. So here sin theta is approximately theta. So mg L theta, this is I alpha. So from this we can find alpha upon theta equals to mg L upon I. Now I is what? I is the moment of inertia of this bob along these axis. ये पॉइंट के अराउंड जो एक्सिस है उस एक्सिस के अराउंड ये बॉल क्या हो रहा है? रोटेट हो रहा है, राइट? दिस एक्सिस, दिस इज एक्सिस, दिस इज स्ट्रेट एक्सिस, एक्सिस ऑफ रोटेशन. इस एक्सिस ऑफ रोटेशन के अराउंड ये बॉब क्या हो रहा है? रोटेट हो रहा है. सो दिस इज एक्सिस ऑफ रोटेशन. अब I is what? I is the moment of inertia. Now what do you mean by moment of inertia? How to find this moment of inertia? So moment of inertia is generally the product of mass of the object and the square of its perpendicular distance from the axis of rotation. अगर axis of rotation ये है और bob ये है तो इसका perpendicular distance is generally just only the length of the pendulum, right? So this is the axis of rotation, this is our ball, the perpendicular distance, this and this, the perpendicular distance is generally just only the length of the pendulum. So the length of the pendulum is the perpendicular distance. Now what do you mean? What will be the moment of inertia here? So moment of inertia is into perpendicular distance wala square. So ml square. So I can put this value here. So alpha upon theta equals to what? Mgl upon I. That means mgl upon I means ml square. So get cancel, ll get cancel. So alpha upon theta equals to g upon l. But in previous slide we have seen that the time period is given by 2 pi under root of theta upon alpha in angular SHM, right? So अगर अल्फा अपॉन थीटा g अपॉन l है यानी थीटा अपॉन अल्फा क्या आ जाता है? थीटा अपॉन अल्फा इज अंडर रूट ऑफ l upon g. So we can put the values here. So time period equals to 2 pi under root of theta upon alpha means l upon g. So this is the time period of the simple pendulum performing angular SHM. So from this we can see that the t is directly proportional to the square root of the length of the pendulum and the time period is inversely proportional to the square root of acceleration due to gravity. Yani we have seen the angular SHM, right? Angular SHM means here the restoring torque is inversely proportional, not inversely, it is directly only. The restoring torque is directly proportional to the displacement. Which displacement? Angular displacement from the mean position, and both the torque and the angular displacement act in opposite direction. This is the first thing. Then we have seen one practical example of the angular SHM, that means our simple pendulum. In that we have seen that अगर ये मोशन हो रहा है सिंपल पेंडुलम का, ये एंगुलर मोशन है. अब एंगुलर मोशन है यानी या तो कुछ टॉर्क आने वाला है. अब टॉर्क due to two forces. The first one is the tangential force and the second one is the centripetal force. The centripetal force is what? T minus mg cos theta and the tangential force is mg sin theta. अब जो टॉर्क है ड्यू टू सेंट्रीपेटल फोर्स, that means the torque due to t minus mg cos theta is 0 because the angle between the radius vector, that means the length vector, and the centripetal force is 0. So torque होता है rf sin theta, means the sign of angle between the force and the radius vector. In the first case the angle is 0, so the torque due to centripetal force is 0. The next one is the tangential force. अब tangential force है mg sin theta and the angle between this mg sin theta and the radius vector theta, the radius vector is theta equals to 90 degree and sin 90 is 1. So the required torque is torque equals to mg sin theta into L, that means mgl sin theta. This is the torque, right? So there is only one torque and the torque is due to only the tangential force. अब ये जो torque है mgl sin theta, we know that for the oscillation we take the theta is very small, so sin theta is approximately equals to theta, so that the torque can be written as mgl sin theta, that means the mgl theta, and the torque equals to I alpha, so that alpha upon theta is mgl upon I, and I is the moment of inertia of the bob. Now the moment of inertia of the bob is given by the mass of the bob into the square of its perpendicular distance from the axis of rotation. So I equals to m, mass, and the perpendicular distance is nothing but the length of the string. So m l square. Putting the values, we will get alpha upon theta equals to g upon l, so that the theta upon alpha equals to under root of l upon g. And the period is given by t equals to 2 pi under root of theta upon alpha. So t equals to 2 pi under root of l upon g. From this we can see the period of the simple pendulum is directly proportional to the square root of the length of the pendulum and is inversely proportional to the square root of the acceleration due to gravity. So this is all about the simple pendulum. In the upcoming session will be very interesting. We will study some cases we will study if what will be the period of simple pendulum if the simple pendulum is in the lift and the lift is moving upwards. The second case, what will be the period of simple pendulum if the simple pendulum is in the lift and the lift is moving downwards. After that, we will see some interesting thing. If the simple pendulum is in the moving car, then what will be its period? If the simple pendulum is in the liquid and the liquid has some density, rho, then what will be its period? These are quite interesting examples. We will solve these examples and we will have a deep look in these examples with some interesting problem solving session in the next session. So revise this all the things and revise the simple pendulum. In the next session, we will apply this knowledge of simple pendulum in various cases.